Hey guys, so this is the video presentation for the digital assignment 2 of our subject Computer Organization and Architecture. So in this assignment our task was to analyze a floating point unit from an open access journal using the concepts learned in the COS syllabus. So I chose a journal from IJESRT which had the topic of implementation of area efficient IEEE 754 double precision floating point arithmetic unit using Verilog. So the first question was to explain how the selected paper relates to the COS syllabus or curriculum. So the selected paper discusses the double precision floating point unit. This paper is related to subjects like COA and VLSI as ALU is something that we studied in CAT 1. So we saw different algorithms like Booth algorithm for signed and unsigned multiplication, which gave us a procedure for multiplying binary digits in signed 2s complement representation in an efficient way. So less number of additions and subtractions required. It operates on the fact that the string of zeros in the multiplier require no addition but just shifting, and a string of ones in the multiplier from bit weight 2 power k to weight 2 power m can be treated as 2 power k plus 1 to 2 power m. So in this method, unlike the traditional methods, they adopted a better multiplication algorithm and the addition of a partial product. So the proposed concept provides the additional solution that was able to perform the many operations such as addition, subtraction, multiplication and division with accurate response and effectiveness. In this paper, the floating point architecture consists of 4 subunits, namely addition, subtraction, multiplication and division. So for these units, receive the double precision formatted outputs and performs the operation produces the outputs. Those outputs are selected by the selection multiplexer. That multiplexer will be controlled by using this select signal given by the user. So next, moving on to the next question, the drawing the existing architectures discussed in the paper using appropriate raster graphics editor software in encapsulated EPS file format. So this is the 1-bit ALU block diagram, existing one, and this is the existing addition and subtraction hardware that we have. It consists of a resistor, complementer, adder. So this is the Booth algorithm block diagram, which was taught to us in module 2, I guess, in the COS syllabus. So this third question was to draw the tabulated results and graph using Office Suite in EPS file format. So these are the outputs that the people who wrote the research papers got in Verilog. So I generated the graphs in MATLAB using these outputs. These are the graphs. Next question was to draw the proposed architecture discussed in the paper using diagramming and vector graphics and application software. So this is the floating point unit block diagram. As we can see, this consists of an input which goes to the 4 ALU operations: addition, subtraction, multiplication, division, which again goes to the selection multiplexer, in which the user sends the select signal, which after which goes to the normalization unit, and from there it goes to the output. So this is the block diagram of addition and multi subtraction algorithm. So here we have the exponents. Here then we check whether E1 is greater or even E2 is greater. Then that signal is sent to the two multiplexers, input multiplexers that we see here, where E1, E2 is given to those the inputs. 2 cross 1 multiplexers are there. Now we check if is large or small. Then it is sent to the select line SE SL is equal to EL minus ES, the two outputs that we get from the multiplexers. Now this is sent for further subtraction. Now this is the multiplication architecture. Now the fifth question was to draw the transistor level internal diagrams using electronics schematic capture and simulation tools in EPS file format. So these are the transistor level internal diagrams for the multiplication unit basically. Sixth question was to compare the proposed architecture with existing architectures in our reference books. So the addition and subtraction algorithms used here are almost similar to the existing architectures discussed, but the main improvement is seen in the multiplication algorithm. So for performing the floating point multiplication, there are some basic steps to be followed. Those steps are, for the proposed architecture, what happens is first a multiplication of the significand happens, then placing the decimal point in the result, adding the exponents, obtaining the sign, normalizing the result, rounding off the result to fit in the available bits, and checking the underflow or overflow if occurrence occurs. Now in the existing architecture, the multiplicand is subtracted from the partial product upon the encountering the first least significant one in a string of ones in the multiplexer. The multiplicand is then added to the partial product upon encountering the first zero in a string of zeros in the multiplexer, provided that there was a previous one. The partial product does not depend or change when the multiplier bits is identical to the previous multiplier bit. So, unlike the algorithm discussed in the reference books, for significant multiplication we use the radix 4 unsigned Booth algorithm because in general we don't deal with negative number multiplication methods because in our multiplication MSB is not concerned with the sign of that particular number. The multiplication is segmented as the partial product generation and tree addition and the final addition. Also, in this Booth recording can be of 3 bits. Each starts for either LSB to MSB or MSB to LSB by the overlapping each group's numbers that are multiplied. By this we can reduce the number of partial products by half. By radix Booth recording technique can be considered as the partial product generation. Exponent addition can also be carried out by the adder, but this resultant added output consists of two bias numbers so that the subtractive circuit can be used to subtract the one bias from the resultant exponent add out. So moving on to the next question. Next question was to list the advantages of the proposed design over the existing design. So the device utilization analysis of double precision floating point unit arithmetic shows that it occupies an area of 13,313 slices. Now Adanki, Purna Ramesh, AVN Tilak and Dr. A. Mallikarjuna Prasad implemented the double precision floating point multiplier and it occupies an area of 5648 slices in comparison to the 13,313 slices, which is a major improvement. So the implemented design provides less area with more accuracy. Next question was to list the merits and demerits of the proposed existing architecture hardware. Merits are less space consumption, less logic cells required, has higher accuracy. Demerits are although less space required, but power consumption boosts up. Now, the next question was to list the applications of the proposed design. So this approach for calculations has many industrial applications in the design of next-gen transistor and chip designs, where you require smaller size with faster calculation. Also used in FPGA implementation. So the last question is to draw the flowchart or algorithm or transistor level proposed circuit, the design in EPS file format. So this is the floating point unit block diagram, which was discussed before. Now this is the flowchart for addition and subtraction algorithm, and this is the multiplication architecture. So thank you.